Hey everyone, welcome back to your math class and to lesson 21. Today is the first lesson of our geometry unit, and we're going to be talking about polygons. So the plan for today's lesson is fairly straightforward. We're going to talk a little bit about polygons for a few minutes, what they are, and some kind of cool stuff that we can do with them. Then we'll talk a little bit about angles after that. Um, After that, we'll get into a little discussion about regular and irregular polygons. And then towards the end of today's lesson, I'm just going to introduce you guys to a little game, like a little app that you can get to help you play around with some of the tools that we use in geometry a lot of the time. It's a pretty fun game. It's good exercise for the brain if you're interested in trying it out. But we'll get to that later on. So we're going to start off pretty simple. Hopefully this is something that all of you have seen before, but just in case you haven't, that's why we're talking about this in our first lesson of the unit, because I want to take things slow so that we don't get overwhelmed in the first lesson or two, and then we can pick up the pace a little bit later on. So first things first, what are polygons? So a polygon is a closed shape with straight sides. Now what does that mean? Sounds pretty straightforward, but so basically it has to be a shape that doesn't have any openings. So for instance, something like this is not a polygon because there's an opening right here, and something like this is not a polygon because it's got curved sides. So neither of those would be considered polygons, but all the shapes in black here would be considered polygons because they're closed shapes, so there's no gaps anywhere, and all the sides are straight. There's no curvy, bendy sides making up any of these shapes. So we've got a whole bunch of different examples, a bunch of different examples of polygons, a few of them with the diagrams. We've got triangles, quadrilaterals, which is a word that you will have seen before if you've studied geometry. But basically it's any shape with four sides, any polygon with four sides. So we got triangles, we got quadrilaterals, we got pentagons, hexagons, and octagons as examples. There's, of course, you see we've got the hexagon, which is a six-sided polygon here, and we got the octagon, which is an eight-sided polygon. There is a name for the one with seven. It's a heptagon, H-E-P-T, heptagon. That's the one with seven sides. That's not shown here just because for some reason nobody talks about it. And so I also left it out of this list here. But yeah, so we got triangles, we got squares, rectangles, trapezoids. Those are all, so squares, rectangles, and trapezoids, those are all examples of quadrilaterals. There are other kinds as well, but those are all examples of quadrilaterals because they are all polygons with four sides. So they're all made up of four straight sides that make a closed shape. And in different, if you do that in different ways, sometimes you get a square, sometimes you get a rectangle, sometimes you get a trapezoid. Then there's also, as we already talked about, we got pentagons, hexagons, and octagons, like in the diagrams over here. Now, this thing with straight sides, when we're talking about polygons and we say, okay, it's a closed shape, closed is pretty easy to understand. You got to have all the different sides fit together so that there's no spaces left over. So you can't have any openings, you can't have a way in or out. If you were a little two-dimensional creature living on your piece of paper, there should be no opening to get into or out of the shape. So that part's pretty clear. The straight sides thing is also pretty straightforward in that it's not, your lines aren't allowed to be curved, the lines that you use to make the sides of your shape. But I wanted to bring this up because I'm not particularly bothered if, when we talk about geometry in this unit, it is generally good practice to be aware of all the different like names of things and the different terminology and stuff. And we're going to talk about some of the terminology, but I've never been one to focus on the right words instead of the right ideas. Obviously, in a perfect world, you learn the right words and the right ideas and everything goes together very nicely. But you'll find that even in the real world, when we talk about shapes like squares and triangles in the real world, we don't say polygons all the time. We say shapes because that's just the word that we use. So as long as you understand what a polygon is, that matters more to me than if you understand uh, the word polygon existing, but not knowing what it is. Does that make sense? So if you guys understand that, okay, a square is a polygon because of these two properties, that matters more to me that you know what a polygon is, but you call it a shape because that's just the word that we use, than for you to say a square is a polygon and you kind of nod your head pretending to understand, but you don't really understand. So we're going to talk a little bit about the terminology just because otherwise it gets confusing later. But we're not going to spend too much time in this unit focusing on the words, because I find that sometimes if you focus too much on the words, you lose the idea behind them. And so I don't want to lose the idea behind them. So to get back to what's on the slide. So this whole business of straight sides, when we're dealing with polygons, and we say that the sides of the shape have to be straight. Now, when you're talking about these things kind of in daily life, you'll call them shapes, and you'll call them straight sides or straight lines or whatever. But in geometry, geometry likes to talk about these things a little bit differently. The straight part is not complicated. It's a straight line. It's not a curved line. We know what that is. But geometry likes to think of lines, and like we can say straight lines, but geometry thinks of lines as being straight, but also going off in both directions forever, to infinity in both directions. So as far as geometry is concerned, if geometry was a person and you went up to it and you said, hey, can you draw me a line? It would draw you a line that keeps going that way and that way forever. And the line doesn't have a starting point or an ending point, and it just goes on forever and it cuts the universe in two. Not great, right? So when we draw an actual line in geometry, obviously we would run out of time and energy and paper if we tried to draw a line that actually goes on forever. So in geometry, when we're talking about lines, you'll see them show up like this first red line going across the screen, which it stretches all the way across the page. Now, when we're doing this, later on, we're not going to draw our lines going all the way across the page. But if you want to show your line as extending forever in both directions, because it's a true line according to what geometry says, then you'll put these little arrows on both ends that indicate that the line keeps going. You just either can't be bothered to draw it out that far, or you've run out of paper or whatever. So that's what geometry considers to be a line. So when we say that, oh, a polygon is a closed shape made up of straight lines, that's not true, because lines go on forever. And your squares, if I asked you to draw a square, I would think that none of you would draw something like this and then put all these arrows here to say, oh yeah, it's a whole bunch of straight lines and they're all extending out infinitely in all directions. Right? If I just finish with my arrows here, and then say, oh yeah, but look, here's my square, right? In this space right here is where I drew my square, right? No, none of you would draw that as your square, right? Everybody would draw probably with lines going straight up and down and then straight left and right, just vertical and horizontal lines. You wouldn't draw it at a weird angle. You wouldn't draw it with these lines that extend forever. You would probably draw your square something like that, right? Now, those lines, if I was a better artist with my computer mouse, would be perfectly straight, but they don't go on forever. So in geometry, if you take a line and then you chop it so that it starts here and it ends here, and it's just a straight line between these 2 points, and then it doesn't exist outside of that, like each of these 4 pieces here that make up the square, then that's what geometry calls a line segment. The segment is just like a piece of something. So it's like a piece of a line. So I just wanted to talk about that because that's something that comes up pretty early on. We're talking about polygons. We're talking about these straight sides and stuff. But if you go and Google it, you'll probably see some places that talk about the sides being line segments. That's sort of the proper term for what geometry would like to call that little shape right there. And that little, it's not even a shape, but that little thing right there, and that one there, and that one there, and that one there, those pieces of this infinitely long lines are called line segments. So a line segment would be like this second red line here on the screen. It doesn't have arrows on it. It only goes so far, but it has a starting point and an ending point. And it doesn't matter whether you know, it's this one is the starting point or that one's the starting point, doesn't matter. So next up is talking about angles. So angles are fun, and we're going to spend quite a bit of time talking about angles probably in our next class. So angles describe how much space there is between two lines. And again, now you can see I'm not being too bothered by the words, because if I say two lines, well, that's two lines that go on forever and ever, right? It could be two lines that go on forever and ever, and there's an angle right here, and there's an angle here, and there's an angle here, and there's an angle here, right? We could talk about those angles in terms of these two lines that intersect like an X, or the way you'll normally see angles talked about is like these angles over here, where it's like two little line segments that meet up at one point, and we're talking about that little space on the inside most of the time. That's our angle. So angles describe how much space there is between these two lines or line segments that are intersecting, which basically just means they're crossing each other, like in this example up here, or they're meeting up at a single point, like in this example down here. And so angles are measured in degrees. So basically we're measuring, if you were to start here and then you kind of climb your way up to the other line segment, that space in between, we measure that in degrees. So you can see we've got some examples of different angles over here. The closer the two lines are to pointing in the same direction, the smaller the angle is. So if I had something like this and this as my two lines, they're very, very close to pointing in the same direction. So this angle in here will be very, very small. But if I have, you know, one line going that way and one line going that way, this is a much larger angle to cover. And that looks a lot more like this guy over here, right? So yeah, so we use angles and we measure angles in degrees to talk about this kind of relationship between the directions that two different lines are pointing in. And it's very useful, and we'll see the utility of it. If you've never worked with angles before, buckle up, because it's going to be fun, but it's also, you know, there's a lot to kind of get used to. So yeah, here we've got some examples of angles. If we ever do get around to trigonometry, the angles 30 degrees, 45 degrees, 60 degrees, and 90 degrees are going to be your best friends for your entire life whenever you do trigonometry. But let's not get ahead of ourselves. Yeah, and there are 360 degrees in a full circle. So we're not really seeing any circles here. It's just a bunch of lines. So let me just illustrate that quickly in case you haven't, in case this is your first exposure to this concept. So you can think of the angle as, and like these changing angles in the diagram on the left there, you can think of it as you have one line segment that's just fixed. So we've got this red line here that's just fixed. And then you have this second line that you attach it right here, but that it can swing around. So maybe it's here and then you measure this angle in that space, or maybe it's out here and you measure that angle, or maybe it's all the way out here and then you're measuring that angle, or maybe it's here and you're looping all the way around. That right there is the circle. That's this whole business of 360 degrees in a full circle. That's this last one right here, this looping all the way around. That is 360 degrees. Once you've made this one full circle going all the way around, that's 360 degrees. Why is it not 100 degrees? Ask the Babylonians. I did not choose for it to be 360, but it's not the worst number to work with, and you get used to it pretty quickly. All right, let's talk a little bit about regular polygons and irregular polygons. So a regular polygon is a polygon whose sides are all the same length as each other, and all the angles on the inside of the shape, which we call the interior angles, are equal to each other. So that's a lot of words. Let's break that down. So a polygon whose sides are all the same length as each other. So for example, if we look at this square here, all four sides of the square are exactly the same length. And that's one of the criteria of a regular polygon. The other one is that all the angles on the inside of the shape, the interior angles. Interior just means inside. So if you've ever heard like interior decorating, it's decorating the inside of a house or of a building, right? So the angles on the inside of the shape. So that means when we're talking about a square, if we talk about like this side here and this side here, they actually make two angles. One angle is this one on the inside, but the other one is this angle on the outside, right? So they make these two angles, and it's really easy to forget about the outer angle. Now, of course, since most of you presumably speak a fair bit of Spanish, if not are fluent in Spanish, Spanish has two words for corner that differentiate between the inside and the outside corner. So it's something that maybe isn't such a strange concept if Spanish is your native language, but when I was growing up, everybody spoke English as their native language, and English doesn't really have different words for these kinds of corners. So yeah, so I just thought that was worth mentioning because we'll be focusing mostly on the angles on the inside. So for the square, we're saying that this angle in here, and this angle in here, this angle in here, and this angle in here all have to be exactly the same, and all four sides have to be the same length in order for it to be a regular polygon. So a square is an example of a regular polygon because all four sides are the same length, and all four angles are also the same as each other. And an irregular polygon would be one that doesn't meet these two criteria or doesn't meet one of them. So maybe you have a shape that's got all the angles are the same as each other, but not all the sides are the same length or something, right? So, or, you could go the other way around as well. So yeah, we've got regular polygons, we've got irregular polygons. If you guys have ideas, if you want to take a guess, maybe if this is super basic, pause the video and talk amongst yourselves and try and name a few more regular polygons, maybe with different numbers of shapes, or different numbers of shapes, maybe with different numbers of sides. Try and name a couple. But that's not the most central part of the lesson, so I didn't put the little pause thing in the corner, and we're just moving right along. So the reason I want to move along, and that's why I want to talk about this right now, is I want to make sure we're all on the same page before we get into the rest of our unit and start drawing out polygons and, having polygons on our homework assignments or in diagrams that I give you on quizzes and tests. And I don't want you to panic when you start seeing all these extra symbols that show up on your shapes. So I want to talk about how we indicate equal sides and equal angles when we're talking about polygons. So if you read the text on the left side of the screen, it says, when we want to show that two sides of a polygon are the same length, even if we've drawn them at slightly different lengths, that happens sometimes, then we put these little tick marks in the sides that are the same length as each other. So what does that look like? So if we look at you could look at the square example, but I'm also going to draw one out here. So the bit I was saying about not drawing it perfectly is, here's my square. All right, but I've drawn this by hand. We're going to ignore that that's not perfectly closed. There's my square, right? Those four sides are probably on the computer screen, probably not the same length as each other. If you took a ruler to them, you'll probably find that this side is probably a little bit longer than that side, right? But if I want to show you that, okay, this is my best drawing of a square, and I want you to do some math with this square, assuming or basically pretending that all the sides are the same length, then what I'm going to do is I'm going to put a little tick mark in all the sides that are supposed to be the same length as each other. So there's my square, and I've put one tick mark in each of the sides, which is supposed to communicate to you that all those sides, because they all have one tick in them, they're all exactly the same length. So that's how we would show that it's supposed to be the same exactly the same side length, even if maybe we didn't draw it perfectly. So an example is if you look at the rectangle, and again, you can look at the diagram that's right below this drawing as well. Here's my best rendition of a rectangle. Again, ignore that there's like curves and stuff in it. I'm drawing with my touchpad on the computer. It's not going to be perfect. But for a rectangle, I'm actually going to draw out two rectangles so I can highlight something. So here's my second rectangle. So I want to indicate that the top side and the bottom side are the same length as each other in this first rectangle on the left, in this one here. So what I'm going to do is I'm going to put one tick mark through the top and one tick mark through the bottom. So that's telling you that the top side and the bottom side of this rectangle are exactly the same length as each other, even if I didn't quite draw it perfectly. And then I also want to show that the left side of the rectangle and the right side of the rectangle are the same length as each other, but not the same length as the top and the bottom. So for that, I'm going to put a different number of tick marks. I'm going to put 2 tick marks in the left side, and I'm going to put 2 tick marks in the right side. So all the sides, both the sides that have 1 tick mark through them, are the same length as each other. So the top and the bottom are the same length as each other because they've both got 1 tick mark. The left and the right side are the same length as each other because they've both got 2 tick marks, but the left side is not the same length as the bottom because they've got different numbers of tick marks. So that's how that works, and it's pretty straightforward. There's no rule saying that like, oh, the longest side has to have the most tick. No. I could have put 1 tick mark on the top. I could have put 2 tick marks on the top. And then similarly, I could have put 1 tick mark on the side instead of 2. It just needs to, you just need to be able to communicate that the top side and the bottom side are the same length as each other, and the left and the right sides are the same length as each other, but not the same length as the other two sides. So there's no rule about like, oh, you have to put 1 tick mark on this side and 2 on that side. You can do it however you want, as long as you are communicating this same idea. And I'm going to show you why this is useful on the next slide, but I'll just give you a sec if you want to pause and you can take a look at this graphic right here. It's just got some more shapes and it's got some more stuff going on with the tick marks, but we're going to move on. So why is this useful? It's useful because suppose I give you guys a test question, and we're going to ignore the letters right now. We'll talk about how we label our shapes and lines and stuff later on. But let's just look at this pentagon in the middle, right? Pentagon because it's 5 sides. Let's look at this pentagon in the middle. I'm going to redraw it out here. Suppose I draw by hand a pentagon for your test. Don't worry, we're not anywhere close to a geometry test. But suppose we've got a pentagon like this for your geometry test in like, I don't know, a month, right? And I want to tell you that it's a really badly drawn pentagon. If I was trying to show that all the sides are the same length, it's a really badly drawn pentagon. But if I wanted to show you that these 3 sides are the same length, then I'll put a tick through here, a tick through here, and a tick through here. That's telling you that those 3 sides are supposed to be the same length, but it doesn't tell you very much else. The only thing it tells you, so you know that this side is exactly the same length as this side, even if I didn't draw it perfectly. This side is the same length as that side, even if I didn't draw it perfectly. But also, all of these 3 sides here, they're all a different length from this side up here, and a different length from this side over here. Now you could say, okay, well, maybe if 1, 2, 3, if those 3 sides are all equal, then maybe those 2 sides are equal to each other. That's not safe to assume. And you guys, if you'd like to pause and talk about it and try and figure out why it's not safe to assume, then you can go ahead and do that. I'll give you a sec. But why it's not safe to assume that those top 2 sides are the same length as each other is because if they were, then I would have done this. I would have put 2 tick marks through each of them to say they're both the same length as each other. This way, I'm telling you that this side is the same length as this side is the same length as that side, but these two sides are the same length as each other, but different from the other three. But if I haven't put that up there, if I haven't put those extra tick marks up there, then what that might be telling you is that this side and this side are different lengths from each other. And it's pretty hard to see that if I've just drawn it out on your test and I've just drawn out a pentagon by hand. Firstly, you don't know, was this supposed to be a regular pentagon? Are they all the same side? Or are three of the sides the same and the other two are the same as each other? Or are these three the same and then that's different and then that's another different side length? That's what the little tick marks communicate. And I don't care if you wanted to put, I'm just going to get rid of the arrows on the outside. Oops. Well, there goes my pentagon. Let's redraw those two sides. Oh, geez. Let's redraw that right there, and then that right there. Suppose this is our pentagon, right? If you wanted to say, put two tick marks here, here, and here, that doesn't change anything. All the sides with the same number of tick marks are the same length as each other. But you have to be careful not to assume that the top two sides, just because they both have 0 tick marks, I should have said that earlier, 0 tick marks is the exception. You don't necessarily know if they're the same length if there's no tick marks whatsoever. So if I wanted to be super clear that those two sides are different lengths, I'll put 1 tick here and I'll put 3 ticks here. So to make it super duper clear that this side up here and this side here are different lengths from those 3 sides down there. And the same thing can happen in a less obvious situation, right? If I give you a word problem, and we talk about this later, of, you know, some guy who wants to put like a fence around his pool or something, and then I ask you to figure out like the size of the pool. And it looks like it's almost a square, but it might be a rectangle because the left and right sides look like they're a little bit longer than the top and bottom sides, right? If I don't put the tick marks, then you don't know if it's a square or a rectangle. This would tell you that it's a square, right? Because now they're all the same length. Even if I haven't drawn it perfectly, I've drawn pretty much a rectangle there. But if I put those tick marks, that's telling you I'm just a bad artist. That's supposed to be a square. But if I do this, now I'm telling you it's a rectangle, even if maybe before it looked more like a square. So that's why this stuff is super useful when we're drawing out our shapes. And I want to make sure that we're all on the same page here, because when we start drawing things out later on in the class and when we get to word problems and I give you a helpful diagram, I'm going to put these tick marks in there as your little clue that like, hey, these two sides are the same length as each other. And if you don't know this, you're going to miss out on that clue and you're not going to have enough information to solve the problem anymore. So let me know if you have questions about this, but that's why I wanted to spend so much time on this today. And similarly with equal sides, there's also a way to denote equal angles. And we'll talk about angles more and how we describe and classify angles in the next lesson or two. But for now, I just want to talk about showing that two angles are the same. So you saw before when I was drawing those angles, you know, I'd have my line segment here, I have my line segment there, and I draw this little arc, this little part of a circle in between them. If I have two angles and I want to show that they're the same as each other, maybe I do something like this, and I want to show that these two angles are the same as each other, I'll just put a tick mark through that arc. And that tells you that those two angles are supposed to be the same. Now, we'll talk about this like little square inside the square. That's for next lesson. But more so, I wanted to focus on this guy right here. So here we've got the little double tick marks in all four sides. So that's telling us that all four sides are exactly the same length as each other, even if they don't necessarily look like it, but I think they've done a pretty good job of making it look like it. But then for the angles, what they've done is they've colored the arcs green for one of them, and they've colored the arcs gold for the other one. Now, you could do it that way, but sort of the more proper way, just because most of the time you're only writing with one writing implement, a pencil or a pen, but not both, and not like colored markers or color pencils or anything, then what you would do is you draw everything the same color. So all your arcs would be the same color as every other arc. But then how do you show that two of them are the same as each other and then the other two are the same as themselves? You put one tick mark through these two, and then you put two tick marks through those two. For instance, and you could have done 1 and 2 this way, you could have done 2 and 1, like you could have put 2 through the green ones and 1 through the yellow ones if you wanted to, but basically you just have to show with the tick marks that, okay, these two angles are the same as each other, and then with the double tick marks, those two angles are the same as each other. So that's all. It's the same idea as what we had with the squares, or with the equal sides. And it's just for, if I draw a triangle, which is already off to a bad start with that squiggly line, but if I draw a triangle like this, you don't necessarily know very much about that triangle, right? It's just basically all you know is that it's a triangle. But if I say, I'm going to tell you that this side and this side and this side are all the same length as each other, and this angle and this angle and this angle are all exactly the same angle, suddenly you learn a whole bunch more information about the triangle, and I didn't give you any information. I didn't give you any numbers at all, right? But once we spend a little bit more time talking about triangles, you will produce numbers from these tick marks. From this diagram, you'll be able to pull out 3 numbers right away from that triangle. And if you've done geometry before and you've done it beyond this level, then you'll be able to do that already. But for this triangle up here, there's nothing you can say about the sides and the angles just yet. For this one, there's a few things you can already say, and you only need me to give you basically one more number, and you'll know everything you need to know about that triangle. How big the sides are, what the angles are, how much space it takes up on your sheet of paper, how much distance it takes to go all the way around. Whereas for the top one, you can't do that. I need to give you a whole bunch of information for you to be able to do that with the triangle on top. The triangle on the bottom, you're this close to knowing everything you need to know about that triangle in terms of all these different properties that we can use to talk about them. So that's pretty much everything I wanted to talk about in this intro lesson. I think we're doing all right for time as well. So over the next few lessons, we'll explore different properties of polygons, different types of polygons. We'll explore some of the similarities and differences between them, and we'll focus especially on 3-sided shapes or triangles and 4-sided shapes or quadrilaterals. And if that name is scaring you, quad comes from 4 and lateral is like the sides, right? Quadrilateral, 4 sides, 4-sided shapes. That's all there is to it. So it's a bit of a strange name if you've never seen it before, but it's literally just 4-sided shapes. Similar to how triangle is 3, angle, 3 angles. That's it. So yeah, that's what we're going to spend our next couple of lessons on, and then we'll get into more and more complicated topics after that. And just a last thought for today. This is not by any means like a paid promotion or anything, but some of you may have heard of this game before. But if you haven't, it's called Euclidia. You can get it on the App Store or the Play Store or whatever. It's a fun little geometry game, and it might help you get used to some of the ideas that we're going to play around with in our geometry unit. It is pretty tricky, so don't play it right before bed, because if your brain's not working, good luck. But yeah, I just thought I would drop this in here. This isn't a paid promotion. Euclidia is not sponsoring this episode of, it's nothing like that. It's just a game I used to play as a good little brain exercise, and it's a fun geometry game, and I thought I would share it because it's relevant to the unit. So that is everything for today. As always, if you have any questions, leave me a comment, send me a message, Instagram, whatever works. But if there is nothing, if I don't hear from you, then I will see you all in the next video. Have a good one.